Okay, so after this brief discussion or introduction about thermal conductivity and diffusivity, our next question would be how do you obtain these values for different substances? And since we are doing this as an advanced course, it's really important for us to have an idea or to kind of combine the knowledges from modern physics, like from kinetic theories, to see if we can actually predict the conductivity, the thermal conductivity or the diffusivity of gases at low density. So the topic of this discussion is exactly that. So let's go ahead and write that down. We are going to discuss the thermal conductivity and diffusivity of gases at low density. And the core of this discussion is to implement the collision theory of dilute gases. Okay, so from the basic assumptions of collision theory, here are some assumptions for the gas molecules itself. So first would be we would model gas molecules as rigid spheres. Okay, so first we would model gas molecules as non-reacting or non-attracting rigid spheres of mass m with a diameter d. Okay, second, we would assume that there will be no convective motion of gas. So no convective motion of gas. In other words, the overall velocity of the gases, the net velocity, is 0. Okay, and so from modern physics, we know some values for gas molecules if we view them as rigid spheres. Basically, we know that the relation between the mean speed and mean free path is going to be related to the molar mass, also related to temperature. Okay, so we're not going to show you how to derive these, but just going to show you their formula real quick. So now for rigid spheres, of gas molecules, we know that first is the molecular mean speed. Which is using the symbol U bar equals to the square root of A kappa T over pi m. Okay, here the kappa is the Boltzmann constant. And T would be our absolute temperature. We also need the wall collision frequency. Per unit area. Or maybe we can write this on another line. Per unit area, which we use the symbol Z, equals to 1/4 times N times U bar. Here, N is the number density of gas molecules. Okay, and finally we need the mean free path. Which is lambda equals to 1/√2 pi d squared times n. Okay, so you can see that we have given three values here. One would be the molecular mean speed, one would be the wall collision frequency, and the mean free path. So how are we going to start from here to predict the thermal conductivity of dilute gases? And here is the idea behind all the derivations, is that if you think of dilute gas molecules, so we can do some really simple schematic showing you the idea, right? So let's say you have rigid spheres that's representing gas molecules in free space with net velocity of 0. Okay, so how is energy going to be transferred? Let's say if we have energy transferring from here to here, how does energy transfer from x equals to x1 to x equals to x2? Basically, for dilute gases, the energy transfer actually is happening through the sequential collision of these gas molecules when they're viewed as rigid spheres. So if a gas molecule has some kinetic energy, it randomly just collides with another gas molecule here, right? Then this gas molecule would pass on that kinetic energy, right? It also has the probability to maybe, collide on this one, and it pass on the kinetic energy. So basically, you can think of energy transport or energy being transported through the collective collision events not events of gas molecules. Okay, so we say that each gas molecule, so gas molecules individually are moving, right? They're not sitting still in space. They're actually moving, but the net velocity is 0. But if you look at individual gas molecules, they actually have a speed, which is pronounced here. And speed will be related to what? Will be related to kinetic energy, right? So kinetic energy. So basically the energy is going to be transported by giving the kinetic energy of one molecule to the next. Okay, so this is where kinetic energy comes in. Okay, and then to the mean free path is telling us that what is the average distance where a gas molecule would collide to another one, or where collision occurs. Let's put it simply like that, where collision occurs, right? And then the frequency is just basically a measure of the probability, or a measure of the frequency of, how often this type of collision is happening. So the three all add together would give you some kind of idea, the macroscopic